you are going to need your computer to do it, and it's going to be on Wiley Plus, just like your homework. And it's going to cover chapters up to 4. And due date. And you're going to have extra time, so it's not going to be cut short at 1:45.
No, please.
You want to know what's going to be on the hand? We'll come tomorrow to help you. Now, I'll tell you. You want me to tell you? Yes? 1:55-ish. Yeah. Yeah, the class starts at 2. So I wasn't sure if I've changed the time. If I can start at 5 minutes early, that's what I want to do. Is to instead of 12:30, start at 12:25. We're going to be here with the TAs, so just in case, yes. Yeah. You go there with your laptop. Okay. There's this exam and this class is easier compared to the one in the other class. It's just my subjective opinion. I could be wrong. Everybody's different. You should have enough time, so we'll be fine. Okay. Do you want to know what's going to be in the exam?
Yes.
Okay. And the problems are shuffled, and the numbers are also different for each student. So one of the problems has to do with interaction between the atoms, and it is dealing with the force of attraction and repulsion, and to solve this problem, you need to understand what this force of attraction entails, and it has to do with the size of an atom. Okay, so if you have 2 different atoms, you're given one size, you can probably find the size of the other one if you're given the force, or if you're given the sizes, you can find the force, or I think I said enough. I mean, it's a test, right? Fair enough? Okay. Remember how we were doing this calculation in class? I think it was for chromium, we calculated the density based on just fundamental principle of knowing how the atoms are packing, right? And the size and the atomic mass, remember? Okay, so another problem is dealing with a specific element and you know how it is packing. HCC, HCP, FCC, BCC, the problem is about the relationship between the atomic radius and the atomic weight and the density. Yeah. The weight percent and the atomic percent and all that good stuff, right? And volume percent we'll also discuss. So let's say if you have a mixture, meaning if you have an alloy, then let's say we take some spaghetti that we boil, right? And we boil the spaghetti, and in the end, you add some salt, typically, right? So, if you know the quantity that you can in one unit, we can recalculate it into the other unit. And this problem is a straightforward one about the conversion between weight percent and how much you put. Yes? And then remember we were calculating the concentration of vacancies. By the way, does everybody understand what EXP means? Does everybody understand that? It's not the latest version of the Dell laptop or the car that you're about to buy. EXP is exponent. So it's E to the certain power, right? And today we're going to be solving a problem that is dealing with diffusion using the same principle by taking the natural logs of the exponent and making it into the linear function. And remember I showed you that paper with Nate Wolfson, who was working for Air Force, where we measured the evaporation rate of oil and measured and calculated the activation energy. This problem is exactly about that. It's about the activation energy given the given certain parameters of the equation. Whenever we are dealing with exponential dependence on temperature, the temperature is expressed in certain units. What are those units? They're in Kelvin, right? So then the corresponding constants are also going to be in Kelvin, right? And the energy can be expressed in electron volts, or it can be expressed in joules. So electron volts per amp or joules per mole. And that depends on what constant you use, Boltzmann constant or gas constant. It's
Thank you.
it's the exponent of minus the activation energy divided by RT or KT. And the temperature is typically always given in Celsius. So you need to make sure you convert that into Kelvin for the calculation. It's a straightforward way to just make this calculation, and then you can take the natural logs of both sides of that equation. So please make sure you review that and you understand the math behind it of how you can do it. And we'll go over something similar today. Dependent on the density, either linear density or planar density, right? And that's the other problem is exactly about that, is to figuring out the planar density and the linear density for a specific material. So you need to understand different packing, simple cubic, body center cubic, face center cubic, and all those derivations that we've done for the linear density and the planar density and things like that. And again, you can have a equation sheet, whatever you want to call it, a piece of paper you can write it on the sides. And I want you all to succeed and get 100% of this stuff. Should be enough time for you to do it. And I'll be holding your hand. I'll be here. Okay? The other thing I want to bring up is this survey about the AI, as the response rate is very low. And since we already got our feet wet with that, I want to collect the data. So in the other class, the TAs did the survey. So I will ask them to convert them. Please, maybe it's a little cumbersome because for this class, they've done it as just a questionnaire. So on the other one, it's going to be just, you go online and you provide your honest answers. It's an audit. But I want to collect this data. I want to combine this data from the two classes to first of all see what you think about the use of education, use of value, if it doesn't make any sense. You know, there are only 2 papers I've read so far about the use of notebook LM in education. And I know people are very cautious, and we all should be cautious. I have another neighbor. It's so easy. There's also one case. There's one video went viral, and it's a song. It's the first time. Oh, by the way, there's another tool called Paper Banana that Google released, and it is very useful for making graphs and illustrations. My personal take on all this is the graphical representation. Actually, it is banned in most of the scientific journals. You're not allowed to use AI to make anything graphics related. And I have mixed experiences but I tell you what the value is. The value is that even if it's not right, you have an idea of what it looks like. What you don't realize is that, or maybe you do realize, especially if you ever, how many of you have been in South Korea? You've been to South Korea? You've been to what city? Seoul. Okay. Is it different than Tampa? How long did you stay there? week. Have you been to the Jeju Island? No? Do you expect Jeju Island to look different than Seoul or not? Okay. They have the saying, a picture is worth 1,000 words. And we learn by copying. You know, when first time I was told to write a paper, I shit in my pants. I didn't know how to do it. I was very scared. And I always thought that if there's a scientific paper, there must be an equation in it. And so if you look at my first papers, they all have an equation. It's not necessarily true. There's no need to have an equation. There's no formal requirement to have an equation. So even if it is wrong, and at this point, the pictures that ChatGPT or other systems can generate for you are typically wrong, it gives you an idea of what it may look like. And then of course you get the funny parts where, you know, the human body is twisted 180 degrees. My recent experience was analyzing XRD data, and the Excel spreadsheet had like 2,000 by 2,000 values, and I submitted that to Manus, that Facebook, Meta, just purchased for $2.5 billion. And Manus gave me the results, and then I did this, and then I started analyzing it. And I did the same analysis in Claude. And in Manus, the data looked like this. So it approximated both, the curve looked like this. In reality, it was like this. So it had certain curvature to it. And Claude did a much better job, but it does not mean that Manus is not good. It depends on what you're trying to do with it. So again, at this point, it could be garbage knowledge that you don't really need, because what value does it have if you're not doing anything with it? But I'm working on a problem right now where this graph was generated schematically, and once you have an idea of how the graph should look like, then you can use your real data to plot it, and that's where the value is. Okay, we discussed diffusion last time, and the diffusion is applied in many different processing steps to control the process, to control the structure, to control the properties. You can see here an example of a gear that was subjected to case hardening. It looks darker on the outside. The reason that it looks darker is because there's high concentration of carbon at the surface. And once it was cut, you can actually see the skin layer. So that's how far carbon diffused, and it changed the properties. And doping we talked about, we'll talk about more when we discuss electrical properties of silicon. And we talked about the diffusion rate. So there is transport of atoms, and atoms have a weight associated with them. So they move from one place to the other place. And if we plot the mass that's diffused versus time, you know, and if it is linear, typically it would be linear, the diffusion rate will be proportional to the slope. So we measure it as a flux, which is the mass of the diffused atoms or molecules divided by the area and divided by the time. The time is a very important parameter. You know, You will all get 100% if you had a take-home exam. Have you ever had a take-home exam? What do you think about that? You like it? Why? Because you can rely on the audience for the solution, or you can make a phone call to your friend, or
Yeah, actually.
no stress, less stress. Man, at the University of Minnesota, in graduate school, the take-home exam, oh, they were brutal, because even professors didn't know how to do it. You know? I used to have those dreams when exams were very stressful. And the reason they're very stressful is because you're constrained with time, you know, and I sympathize. Once you graduate and you get a job, there'll be stress, but different. So, how is this diffusion rate measured? It's measured through a thin membrane. But because there's area, you need to know what area, right? And the driving force for diffusion, any kind of diffusion, is what? Why would things diffuse? What's the driving force for diffusion? Yes. Higher concentration to lower concentration. Does that make any sense? So this is called concentration gradient. Concentration gradient is a driving force for diffusion. So it is measured in kilograms per square meter per second. And the first type of diffusion is called steady state diffusion. And steady state diffusion means that the species are continuously supplied to the site where the diffusion occurs. And in this case, flux J is proportional to the concentration gradient, dC dx. C is the concentration, x is the diffusion direction. So here we have a thin membrane, and here is the position x1, and this is x2. And on one side we have the concentration C1, and on the other side we have concentration C2. And in this steady state diffusion case, the first Fick's law states that the flux J is equal to minus d, the diffusion coefficient dC dx. And if it is linear, which we can assume it is linear, because the membrane is very thin, we say that dC dx is equal to delta C delta x, and that's equal to the C2 minus C1 divided by x2 minus x1. Can somebody tell me, in principle, why there's going to be different concentration on the other side? I want to make an analogy into some physical process. Let's say you're making that spaghetti. What do you need to boil spaghetti? Water. Okay, well, it's raining outside. Where do you need the water? In a pot. Yes, you need water in a pot. How does water get into the pot? How does water get into the pot? You put it into the sink and you open the faucet. And then it fills up eventually. So do you see, even in this process of filling up water into your pot, it takes a certain time. But you can crank the faucet all the way so that you get the maximum water flow. And even if you have another pot that's full of water, imagine you take this pot of water and you have an empty pot over here and you just flip it like this, and this water goes down. It still doesn't happen instantaneously because the water somehow has to flow, right? How many of you have ever baked? Okay. Well, what do you use for baking? Flour. How many of you have ever sieved flour? How does that work? How does that work? How do you sieve flour? Through a collar, and then if you just pour all of that powder in there, then what do you need to do? Why do you need to shake it? It piles up if you don't move it, so you have to go like this, right? And then you're limited of how much powder you can sieve, right? It depends on how violent you're shaking it. It also depends on the size, right? But the powder cannot go through directly, okay? So think of diffusion as sieving powder or pouring water into the thing to make your spaghetti. And the first steady state type of diffusion is when you keep giving it the powder or you keep supplying it. You never run out. Does that make any sense? So here we have a differential equation, which is relatively straightforward. This type of configuration is not very common in nature. And we're going to consider this example of a glove. Methylene chloride is a nasty chemical. It's one of the ingredients in the paint remover. And it can go through your skin and cause all sorts of health issues. You don't want to use a paint remover directly. So you protect yourself. How do you protect yourself? You need gloves. And first we're going to try to see if butyl rubber gloves, which are 0.04 centimeters thick, or kitchen gloves, are adequate enough for the job. By the way, some of the production grade gloves can be very expensive. A friend of mine works for this company called IPA, and this company belongs to Roper, and they manufacture computerized dispensers for scrubs or professional clothing for hospitals, and it's an expensive machine. It could be $100,000. So the doctor or the nurse goes in and they scan their badge, and the system knows their size and it gives them the scrubs. And Tesla is using their equipment, although it's designed for hospitals. And another company is using their equipment that dispenses gloves. Because for the worker, they need to use gloves, but the gloves are $80, so they're not getting new gloves every time they come to work. They get a set of gloves, and those gloves are supposed to last for a certain amount of time. And that's why it is economical for the company to invest in the dispensing machine. Recently, one doctor, a neurosurgeon, made a video of how he can cheat the machine by taking his pants and separating them like this, because the machine gives you the pants and it gives you the upper side. And he figured out that he can take just the pants and put it in the machine in two different containers. Then the machine will give him a set of the whole scrubs. And the video went viral for 5 million views in 2 days. And this was an opportunity for the company to advertise their services. But instead, the corporate decided, oh, it's not good publicity, and they shut this guy down, and the guy took it down because he didn't want to get sued. A neurosurgeon that figured out how to cheat the dispensing machine. Anyway, so what we're going to do is we're going to figure out if it's okay to use 50 cents gloves or $1 gloves. The maximum allowable flux for a 150-pound person has to be less than 3.5 10 to the negative 7 grams per square centimeter per second. And we're going to calculate the diffusion flux of methylene chloride through the gloves. Here we have a glove. We have the paint remover that ended up on the glove. And in this particular configuration, it is assumed that there's an infinite amount of that stripper, paint stripper. Do you understand why? I mean, one drop is super toxic. You cannot just leak it, or that has to be properly disposed of. So the flux J is equal to the minus D times dC dx. We have C1 and we have C2. The concentration C2 is 0.44 grams per cubic centimeter, and C2 is 0.02 grams per square centimeter. You see how big difference of the gradient there is. And the thickness is 0.004 centimeters. And we plug everything into this equation, and we get 1.16 10 to the negative 5 grams per square centimeter per second. 1.16. And the allowable has to be less than 3.5 10 to the negative 7. So you can see that this is 30 times the allowable flux. And it means that these gloves are not going to do the job. Which is why when you're dealing with chemicals, you have to use proper protection. Yes? Does this make any sense? Okay. Well, how does temperature affect diffusion? You have seen a similar equation, except that there we were calculating the concentration of vacancies, which you will do on the test on Tuesday. But here, the diffusion coefficient has exponential dependence on temperature. It's equal to D0 times E, exp means E to this power, minus Q sub D over RT. Q sub D is the activation energy in joules per mole. R is the gas constant of 8.314 of joules per mole per Kelvin, and T is the absolute temperature in Kelvin. So how do you convert Celsius to Kelvin? You add 273 degrees. Now, what I want you to realize, and you know, because of the different scales, there's Fahrenheit, there's Celsius, and there's Kelvin. They're all degrees. But these are different degrees than the measurement of the angle, because angle is measured in degrees, just different kinds, although we use the same word. Weird, isn't it? And basically, the temperature, we can measure how much diffused versus time. So it's going to have the exponential function. And to solve this, we need to transform the data and this equation by taking natural logs of both sides. And if we take a natural log of the exponent, natural log has the base which has e. The natural log is basically a power. There's decimal log where the base is 10, and there's a natural log where the base is the number e, which is equal to, what's the value of e? 2.7 and, okay. So if we take the natural log of this exponent, the natural log of the exponent is the power. And that's why we get Q sub d over RT by taking a natural log of the exponent. And what is the natural log of a product? The natural log of a product is the sum, right? And where did you learn that? Where did you learn that? I think you see it for the first time. Don't tell me you see it for the first time. You see it for the first time? You see it for the second time because I already showed you this when we talked about vacancy concentration. Did anybody know this before seeing this here in any other class? No? Okay. I'm very happy to teach you this. It's my honor. If you just knew. If we all just knew. And I learned this, you know, there's a difference between learning and learning, you know. People have different ways of learning. Somebody's better listening, somebody's better seeing, somebody's better doing. Doing works with everybody. Like if I want to teach you something and we do it together, that's probably going to be the best way. But I truly learned the meaning of Arrhenius equation and this transformation when I did this project with Seagate. But the rule of thumb, you know what the rule of thumb is? That Seagate used before they hired me to do this research project for them. They said the reaction rate doubles for every 10 degrees increase in temperature. And I demonstrated that was not the case by actually making the measurements. It could be either or. And then you have to worry about boundary conditions. Anyway, any question about this? I can pull up that paper again. Should I? Well, let's first look at the data. This is the diffusion coefficient that's plotted as 1 over T, or actually here it is 1,000 over T, and this is 1,000 Kelvin. And what you see here is called a double X plot. On the bottom, you see 1,000 divided by divided by T, and on the top, you see the actual temperature in degrees C. And because the bottom is 1 over T, you can see that on the top, it's not linear. So this is 300 degrees C, this is 600 degrees C, this is 1,000, this is 1,500. Good luck making a plot like this. You need the software to make the plot. What software do you make to make graphs and plots? Excel? Okay. You can make plots in Excel. You're going to spend the rest of your day making sure that they look good. Excel is a great tool for making calculations. So I make those calculations and then I use the graphing software to make the plots. Anybody have ever used anything else but Excel? What? MATLAB. Whoa. Yes. It's a very advanced tool. Anybody else? MATLAB is good and you have a lot of control of how the graph looks like. This is iron in iron. Iron and gamma iron. This is iron and alpha iron. What can you say is the difference between these two data sets? One's at a higher temperature. Why is that? Think. Why this data doesn't go in this direction? What do you think the reason is? The graduate student got tired and never measured? You think that's the case? Do you remember we talked about polymorphism? Maybe actually in this slides or maybe the previous set of slides, that one phase changes into the other, right? So gamma phase only exists in this temperature range. That's the reason. It's a very obvious answer, but I want you to kind of... All right, and then this is alpha, right? This is aluminum and aluminum. And why does this data stop here around 600 degrees C? Why doesn't it go here? What happens with aluminum at 600 degrees C? Yes, who said? Yes, it melts. So we cannot look at diffusion of aluminum and aluminum in the solid state because it becomes a liquid. Yes? Okay. And what can you say about carbon diffusion in iron? Well, you can see that this is carbon and gamma, so this doesn't seem right because you can see when we're going to talk about the phase diagram of iron, like it definitely is here in a different temperature range. So why these two kind of like don't coincide? And the same thing here. So this may be an extrapolation. But what can you say about carbon diffusion in iron compared to aluminum or iron in aluminum or iron? And what is the reason? Is 10 to the negative 8 more than 10 to the negative 20? Yeah? So the diffusion rate of carbon in iron compared to iron in iron is what? Higher or lower? It's higher. And what is the reason for that? Why is carbon diffusion? I like this. Yes. Well, what does that mean? Which one is smaller? Carbon. And as a result, easier to diffuse. How easier it is to diffuse? And why? This is principle and fundamental. I already told you this, but it didn't go through, or it didn't get, anyway. I want you to figure out this answer because we already discussed it. There are two types of diffusion, substitutional and interstitial. What is the difference? What is the mechanism for substitutional diffusion? The answer is in the word substitutional. What substitutional means? Huh? Have you heard about a substitution teacher? What does that mean? You switch out the teacher. You get a substitute. And what does it mean for the atoms? In different order, what does that order mean? Position is still the same. Like, same seat is occupied, but just by a different atom. Or maybe the same atom, in case of iron and iron. And that game we talked about, the puzzle game. Okay. And if the atom is small enough where it does not need to have a space, it can go through. Right here, I see a channel. You know what a channel is? What's a channel? Right here. But it only starts from you. I don't know why. With this pitch of this chairs, I see a straight channel, not all the way to the end, but between the chairs, there's a straight path. We can take a rope and go all the way over there. That's a channel. That channel ends. So imagine that you can teleport from your seat over there because you're very small. It's still going to take you time to do that. But you are going to bypass all of those seats. You're going to go through the channel. I just came up with an analogy. A fast drive lane, what is it called? The fast lane. Yeah, you pay money to go and it's fast. Because there are supposed to be less cars because people are supposed to pay. That's the reason. Now, there's VMSC, which if there's time we'll pull up. Virtual material science that deals with diffusion. Again, this is reciprocal of the temperature. Typically, it's plotted as 1,000 over Kelvin, and the reason is so that this does not become, thousands. So it's 1 and 1.5. So this is actually 1,000 Kelvin. This is 1,500 Kelvin, and it's increasing to the right, because this is inverse. This is the actual temperature, and you see that it is nonlinear, right? 300, 600, 1,000, 1,500, and it's not logarithmic either. So it's a very weird 1 over x scale, and I can tell you that if you try to make a plot like this in Excel, I may not be able to do it. What do? You cheat. Well, you don't cheat. You you calculate physically where the sticks are, and then you put a text box that looks like this. That's what you do. That's what I would do if I didn't know how to use the software. And you don't know if the software can make a plot like this. A certain software to make graphs is $1,000 or $29 per month for subscription. I'm not going to name the software, although I should be naming the software. Because you see the 0 over here? I hate this 0. I hate it. Why do I hate it? How is this significant here? What significance does it show? It's because of a certain software that the company charges $1,000 that has shitload of bugs, and it's my choice not to buy this software as a consumer. I called them in 2010. I said, can I get rid of the zeros? Can you get rid of the zeros? The company has a zero in their name. I'm not naming the names for the software. They implemented this in the version 2020, so it took them 10 years. And there are two options that say 0 is 0 and no trailing 0. 0 is 0 is, if it goes to 0, it will say 0.0. So that 0 is 0 means 0, not 0.0. And trailing 0 is here, 1.0. And if you see a plot like this, I know the software that it was made in. And because it's so expensive, people tend to steal it. And they get bad karma if they steal it. And I try to explain to people that if you steal software, there's no difference than stealing this computer. I could easily take this monitor with me and probably get away with it. You know how ridiculous this is? I'm sorry, but like in certain cultures, in certain countries, it's okay to have bootleg software. I should not be preaching to the choir. How many of you have ever used the software that you didn't pay for? Legally, I mean. There's a trial version. Every company would give you the trial version, so you can try it. And you know what's another trick? Is to give the software for free to the students. It's great marketing. You know why? Because when you know how to use the software and you go into the workforce and you say, buy me this software. You're a company, you have the money. How much is a commercial license of SolidWorks? Please look it up. Please look it up. And how much is Office? SolidWorks is $3,000 per year. Okay. How many of you are mechanical engineers? Okay. Do you realize that you can get SolidWorks for free? Every year, SolidWorks gives us a code, and you can use it for free instead of $3,000 per year. It's a very powerful piece of software. If you want to do what it can do, it can even do finite elements. It's worth $3,000 because you can make much more money with it. And it's given to you for free, so you can learn it. And if you have a skill to do something in SolidWorks, you can get a job because of that skill that you can use SolidWorks. Does it make any sense? You have to realize, I mean, we have three majors here, right? Mechanical, civil, and industrial. No electrical. That's it, right? Three. And at a certain point, you're going to graduate, right? And after you graduate, what do you want to do? To make something that others can't, having certification, passing FE exam, or getting a license, becoming a licensed engineer, which you can in the state of Florida or in the state of Texas. So just think about that. All right. This is a typical problem, and we're going to go over the solution. And this is very important. Typically, you're going to be given data, or you're going to measure data at two temperatures, because things change with temperature, right? You're going to have the diffusion coefficient at two temperatures, T1 and T2. And what we're going to do is follow this procedure of taking natural logs on both sides of this equation. So we have log of D2 is equal to log of D0 minus Q sub D over R times 1 over T2. And then at temperature 1, we have natural log of D1 is equal to natural log of D0 minus Q sub D over R, 1 over T1. And then we subtract this equation from this equation. So this becomes log D2 minus log D1 is equal to the log of D2 minus D1. Where does this come from? Yeah, so that's where you learn this stuff. Which grade? 7th grade, 1, which is equal to the D1 times the exponent of minus Q sub D over R, 1 over T2 minus 1 over T1. Several tricks here. Trick number 1 is what? No, because I already give you the solution. You don't have to know it. It's nice if you know. Temperature is expressed in what units? Kelvin. And you're always given the temperature in Celsius. So please, like, I don't know, make the conversion before you do the calculations. Let's do an example of a diffusion problem. At 300 degrees C, the diffusion coefficient and activation energy for copper and silicon is 7.8 10 to the negative 11 meters squared per second. And the activation energy is 41.5 kilojoules per mole. Calculate the diffusion coefficient at 350 degrees C. So, we'll plug it into the equations. D2 is equal to the D1 times the exponent of minus QD over RT, 1 over T2 minus 1 over T1. Boom! The most important step is this. 300C is converted to Kelvin, 573 K. 350 is converted to Kelvin, plus 273 K. We plug everything into here, and we get 15.7 10 to the negative 11 meters squared per second. And it's roughly like a factor of 2 difference. So diffusion of copper into silicon is going to be faster at 350 than at 300 by a factor of 2. This example has very important technological implication. You know what it is? Processing time of what? Where do you see copper and silicon? Chips. Yeah. The first Pentium processors that came out were still using aluminum. And my PhD thesis at the University of Minnesota, Department of Chemical Engineering and Material Science, was about copper adhesion to silicon. Copper doesn't stick to silicon very well. Aluminum does. So it took the industry 10 years. The first company that made this quantum leap was IBM. And then Motorola, Intel, AMD, and so on and so forth. This is the reason why you have your smartphone in your pocket. That is super powerful. It's because of copper. And when you go to your apartment, what is the wiring in your house? It's copper. And many, many years ago, it used to be which metal? Aluminum. So, just like the house was switched from aluminum to copper, the same happened in semiconductor manufacturing. It takes a lot of people to develop a technology. And a lot of jobs are in the semiconductor industry. And it's high-tech industry. Try to live without your cell phone for a day. If you go to a different country, like Korea, those guys are very tourist friendly. How are they friendly? Did you install Kakao? You did. How long you stayed in Seoul again? 1 to 2 weeks, and she installed Kakao. Does anybody know what cacao is?
No.
You like drinking it in the morning, I know that. Every country has their own, you have Facebook, Instagram, X, Twitter, whatever, right? What do you use here? Do you ever use anything for taxi? Uber? What about Lyft? Have you ever heard about Bolt? Have you ever heard about Yandex.Go? Okay. Have you ever heard about WeChat? How many of you have WeChat? Why do you have WeChat? Why? Ni hao. You arrive in a foreign country, like I came to Vietnam, and there's a taxi there, and I get into this taxi, and it's like 2 miles, and they charge me $30, and that was a ripoff. So they run a little scam. It's official taxi, although it is not an official taxi. Another one is a payphone in Italy. How many of you have been in Italy? Okay. You get in the airport and you see a US looking phone. So you pick up and you make a phone call at $3 a minute. It happened to a friend of mine. Because the phones in Italy don't look like a US phone. So somebody was very smart. Oh, you got to make a phone call. You just arrived. You know? How did I get on that subject of this cacao? I did not install cacao. I had a friend that had it. Have you ever spilled water? Or let me ask you this. When you took a shower last time, was there water on the floor? Okay. And when you come home, is there water on the floor? Where did it go? Evaporated. So water evaporates. Every liquid evaporates, including oil. So in this case, this is the rate of the evaporation of oil or whatever. And it's equal to a constant times, see, I didn't write it as EXP, I wrote it as E, and this is a minus sign, E over RT. And then you take the natural log of both sides. And this is paper in conference proceedings. You will not be able to publish this in the research paper, I'm sorry, because this is basic. They will tell you it's in the textbook. Don't bother us, we're scientists, we know this. Everybody knows this. Why do you bother? But here's the actual data that we measured. So this is the, oh, look at that. I did make this graph. And how did I cheat? Know how I cheated? I don't remember. Or maybe I didn't cheat. Or maybe the software allowed it. 60, 100, 140. And it doesn't coincide. Oh, it does coincide. Shoot. I did cheat. That's exactly what I did. You can see these ticks are, no. I don't remember honestly. It was a while ago, 2007. But you see this slope here? You can fit a straight line to your data. And once you fit the straight line to your data, this slope is minus the activation energy over the gas constant. And that's where all these values come from, right here. For static and for dynamic test. For static test, we just kept temperature constant for 2 hours. You know who may be interested in this kind of experiment is McDonald's or whoever is doing French fries, because that oil evaporates and they have to add some. There's not that much science though. When they see it's getting low, they just pour some more. No need to pay a PhD. Okay, The flat tire diffusion. I call it the flat tire because the second type is called non-steady state diffusion. Like in the beginning, there's very large stress concentration or concentration gradient, and then it decays with time. And I'm going to do this.
Ow.
You have a flat tire. The tire just got a hole. The pressure difference inside the tire and the atmospheric pressure is what? 30 psi. I have a bicycle that's 70 psi, pounds per square inch. Huge pressure. And what's the atmospheric pressure? 1 atmosphere, and how many pounds per square inch is that? Somebody please find out how many pounds per square inch is 1 atmosphere. Okay, this, what is it? I'll just look it up. You think I'm going to trust you? No. I want the number. So, this is the second Fick's law. And the second Fick's law is dealing with non-steady state diffusion. And here, the concentration changes with the position and time. So, the change in the concentration gradient with time is equal to the second derivative of the concentration gradient with distance. And this diffusion coefficient is assumed to be independent of the concentration. So this is a major difference. And here's an example. We have a copper bar, and we have some carbon atoms that are arriving at the surface here, and they diffuse into this bar. And initially, the concentration gradient versus position looks like this. All of this copper here, but then it starts to diffuse into the bar. So this is time 1, this is times 2, this is time 3. It changes with time. So this concentration profile is becoming a function, right? So at time t, the c is equal to c0 between 0 and infinity for x. When time is greater than 0, the concentration gradient becomes cs for x being equal to 0. This is initial concentration, and then it goes to 0 when it's infinity. And honestly, in between, we don't know. We can't measure it. And the difference is because here we assume that the concentration is linear, like this, and the membrane is very small, and we have an infinite number of species that arrive. I always say that students in material science don't really need to know math, because there's only one differential equation in the whole course, which is the second Fick's law. This. And the solution is actually provided. So to solve this differential equation, right, you have the second partial here. It is solved as error function. So this is c of x and t minus c0 divided cs minus c0 is equal to 1 minus the error function of x divided by 2 square root of dt, where t is the time and x is the distance. And ERF out of z is an error function. How many of you have ever heard about error function? Where? Which course? Yeah. You've seen it before. Anybody else have ever seen error function? First time. That's good. You're learning something else as well. It's good. So error function is a tabulated function. For any particular value of whatever the argument is, you can get this function. So there's no need for you to solve this differential equation. You just look up the values in the table. This is C0, this is CS, and this is C of X and T. And you can see that at every position on this curve, it is changing as a function of time and temperature. This is CS minus C0. It's in the denominator. FCC iron carbon alloy, which is called steel, initially had 0.2 weight % carbon. It's carburized at elevated temperature, and in atmosphere, which is the surface of carbon concentration, is maintained at 1 weight %. That was that here that I showed you with a darker layer on the surface. If after 49.5 hours, the concentration of carbon is 0.35 weight % at a position of 4 millimeters below the surface, determine the temperature at which this treatment was carried out. 50 hours is like 2 days. You realize? And in 2 days, it only went down to 4 millimeters. Well, that may be enough. T is equal to 49.5 hours. X, the distance, is 4 millimeters. So 4 times 10 to the negative 3 meters. Cx is the initial concentration of 0.35 weight %. C0 is 0.2 weight %. And Cs is 1 weight %. We plug everything into this equation. And we need to find, we calculate the z, whatever this thing is here. And the error function of z is 0.8125. That's what you need to look up. This is the value that you need to look up in the table. Well, how do we do that? This is the table. So z is 0.9, it goes to 0.95, and the error function is 0.797 for 0.9, and it is 0.95 for 0.8209. We don't have the value of 0.8. What do? We extrapolate. That's the idea. So we assume that it's linear, and then we solve for d to get that the z is equal to x divided by 2 square root of dt. So d is equal to x squared over 4z squared t, and that's equal, we calculate the diffusion coefficient. I'm going to repeat this next lecture after the test next Thursday, but I want you to see this answer, which is 1300 Kelvin, or 1027 degrees C. So if you have 1000 degrees C, it's going to take 2 days to get a 4 millimeter layer of that thing in case hardening. Yes?